I'm not even certain that those who claim to understand it or be experts in the field truly understand it. And we're always learning more. We're always observing more with our findings on what God has created. Where were you when I laid the foundation of the earth? Tell me, if you have understanding. That's Job 38:4. It's one of my favorite verses of the entire Bible. It speaks to this arrogance of us as humans, and God simply reminding us, since you know so much and you have such a great understanding, remind me, where were you when the foundation of the earth was built? Where were you when the sky had stars placed within it? And we all need that reality check. And in the book of Job, Job needs that reality check at that point in time. Speaking to the foundation of the earth, we're going to talk a lot about chemistry today. Chemistry is one of those subjects that tends to make or break someone's career path or their major. In fact, I've seen a lot of students and spoke with a lot of students that actually changed their major because of a course like chemistry. And if you're taking anatomy and physiology, if your interest is in the human body and those sciences, anything within that ballpark at most universities is going to require that you take a chemistry. And I certainly hope that that class, as hard as it can be, doesn't derail you in your goals. It almost did for me, I'll admit. And it's interesting that chemistry was a challenge, and now we're speaking to it because it really ties in directly with anatomy and physiology. And one would think from the outside looking in that if a student enjoys anatomy and physiology, they probably also enjoy chemistry. But one of the reasons why chemistry tends to be non-enjoyable is simply we're not good at it. And the reason we're not good at it is because it's on the microscopic level. It's not speaking to macroscopic things like nose, ear, fingers, those sorts of things. It's speaking to the microscopic level, and we're trying to buy into this periodic table, but we have no life application to know that for sure that exists. And there's a lot of parallels in that. There's a rabbit hole there looking at us in the face right now on how we can believe things that we can't see. And that's the essence of faith and the spiritual life around us. But we won't take that rabbit hole because that's not the topic of today's conversation. Again, in today's podcast, we're going to talk about chemistry as it pertains to anatomy and physiology. And again, if you're struggling with anatomy and physiology, there's a chemistry component that may be limiting you in your anatomy and physiology class. And so I'd like to take you through that. A reminder, as our mission, we bring together Christians who seek to understand their biblical anatomy to connect science with Scripture so we can better understand God's handiwork in our lives. Here again, we have a verse, Job 38:4, that talks about the foundation of the earth. That was even before our own foundation. God is at the beginning of everything, and we're going to understand that episode by episode. Not much of a story for you today, but I do empathize with the chemistry struggle. I remember being a Chemistry 101 student and a Chemistry 102 student and really struggling in a giant lecture hall, trying to find the sense, trying to make sense of everything that was microscopic that was being presented to me. If you went to a bigger university as I did, or you're at a university that is bigger like I was, you could probably relate to that lecture hall and the symptoms, the struggles of that. You can probably relate to a separate lab that's on maybe even the other side of campus with a completely different instructor. I'm thankful for those labs for us that are visual learners and kinesthetic learners. Some of the activities I did in a lab really reinforced my lecture understanding. But lecture in that big lecture hall of 150, 200, 250 students, whatever it was, really was a monumental task for me. And again, I'll admit, it made me think about my career choice, and it made me think about my major that I'd selected at the university. I'm thankful that I didn't change my major. In fact, I added a minor to that, although not in chemistry, and plugged away kept working at it. I finally got through all of my chemistry requirements my very last semester of my bachelor's degree. And you can too. And if your direction again is anatomy and physiology, or that's the course that you're in, let's take a peek at what some of the foundational definitions are for chemistry as it pertains to anatomy and physiology, and let's help get you through the course. So definitions that come up in the beginning of a chapter based on chemistry are often matter and energy. And the definitions are pretty simple. Matter is basically anything that takes up space or possesses a mass. Okay? So anything that we can see is clearly matter. In fact, things we can't see are matter. Things like oxygen, hydrogen, nitrogen, all sorts of different things have an atomic mass, and if they have a mass, they have to be defined as matter. That can be a struggle when it's something that you can't see, which speaks to what we just spoke to, but that's the definition. We then, on sort of the opposite end, have energy, which is not defined as a mass. It is simply defined as its ability to perform work. Understandably so, as concise as that definition is, the concept, the conceptualization of energy is far more complex than that of matter. It takes a giant leap of faith to understand that, okay, we know the outcome, we know movement, we know energy. Physics classes and chemistry classes will often define energy as potential versus kinetic energy. And that's a really difficult concept to understand. I'm not even certain that those who claim to understand it or be experts in the field truly understand it. And we're always learning more. We're always observing more with our findings on what God has created. And I think that's important to distinguish, that scientists aren't revealing something that they made be, right? They're revealing God's creation each and every time there is a new scientific breakthrough. The credit need not go to science. The credit should go to God for creating this all in the beginning. For me, when I think of potential energy versus kinetic energy, I think of a Newton's cradle. Maybe you don't know it by name, but as I describe it, I think you'll know what I'm talking about. A lot of people have them on their desks, and there's like 5 or 6 balls, sometimes more, and you pull one up and you drop it and it hits, and all of them remain still except for the very last one on the opposite end, and it races up and comes back down. So when a person grabs one of the spheres and pulls it up and holds it, the moment they let go, there is a brief period of pause, and that is the fullest extent of potential energy. Because of the influence of gravity, 9.8 meters per second squared, there's only really one direction that this can go, and it's not down because of the connection points it has in this apparatus, so it's going to swing downward and inward, and it's going to collide. When it collides, that's the highest level of kinetic energy. Its speed has reached the highest. So when we talk about potential energy, think of things that are still, but they're sort of coiled up like a spring. And when we think of kinetic energy, think of something that has reached its maximum velocity, like right prior to the collision with one of the other spheres. And that is transferred through, and the process repeats on the other side, and it goes back and forth. Okay, so for me, that's how I think of potential energy and kinetic energy. We then, in that course, or even in a chapter in an anatomy and physiology course, we then focus on atoms and what they are. And most instructors won't tell you the nuance with hydrogen, but they will say that an atom has a nucleus and electron shells. And they'll go a step further and they'll tell you that there are neutrons and protons in the nucleus, and there are electrons in the electron shell. And undoubtedly they'll tell you that neutrons are neutral, there is no charge, protons are positive, and electrons are negative. But rarely at this point, especially if it's a chemistry class, will they tell you about the one element on the periodic table that defies this. And that is the very first one. It is hydrogen. And this is important based on what we talked about 3 weeks ago with acids. Recall with acids, as they donate protons or they donate hydrogen, the reason why proton and hydrogen can be synonymous terms is because The only thing that's in the nucleus of a hydrogen atom is a proton. So if you remove its electron, you have left just a proton. And so you can say things like acids are proton donors or bases are hydrogen acceptors, and they're referring to the exact same thing. When we look at those three subatomic particles, the neutrons, the protons, and the electrons, it is important to note their charge, which we just have, but it's also important to note what changes when we vary their number. So we'll start with the most complex first. When you vary the number of neutrons, you get an isotope. What is an isotope? Well, sodium's probably the easiest example. Sodium is 11, expressed as Na on the periodic table. It's number 11, and that number indicates the number of protons, neutrons, and electrons that it would have in sort of a perfect world. It should be 11 of each, and it would be balanced. 11 plus 11 would be 22, and so we would call that perfect element sodium-22. Why wouldn't we add 11 for electrons? Well, electrons are so small, it's like comparing planets to the sun that they circle, or they orbit, I should say. And those planetary models, interestingly enough, really work well for analyzing these atoms because they behave in a similar way. But they're so small in comparison to the mass of the nucleus that they orbit that their mass is really not considered. It's fractional at best. So we take our 11 and 11 and we call that sodium-22. Now, sodium in that form very rarely exists because of the way that electrons behave. So that 11 that's represented on the periodic table doesn't take into account the electron transfer. So whenever we look at the periodic table, we have to think of sort of a hypothetical element, unless we're speaking to the last column, the noble gases, because they are sort of happy the way that they are and they're stable. But I digress from that. If we change the number of neutrons in any element, we change its isotope. So how do we get from sodium-22 to sodium-23? They're both sodium, but there's just a one subatomic particle difference, and that would be one extra neutron. So in that, you'd still have your 11 protons in sodium-23, but then you'd have 12 neutrons. Again, we're not taking into account the electrons. If you go sodium-24, you simply add another neutron. You still have 11 protons. Now you have 13 neutrons. Okay? So that number 11 for protons stayed consistent between sodium-22, sodium-23, and sodium-24. Because if you change the number of protons, you change the element. Okay, so the next element on the periodic table, number 12, is magnesium. So if you go from 11 protons to 12 protons, you're no longer sodium. You're not in the world of isotopes of sodium anymore. You're now a completely new element, and that element would be magnesium because magnesium is represented by 12. Electrons, what happens if you change electron numbers? Like in the instance of sodium, you simply change the charge. If you recall from your chemistry class or your anatomy and physiology class, they probably spoke to valence shells and electron orbits. The first shell to be stable is 2. So if we start with 11 electrons for sodium, minus 2, now we're down to 9. So we need to go to the next shell. The next shell is sort of happiest or most stable at 8. So we now minus 8 and we're left with 1 from that 9. So we have this last electron shell that just has one lonely electron orbiting it. So if 8 is sort of our happy number, which is where the rule of 8 or the octet rule comes from in chemistry, which I'm sure your instructors have spoke to, would it be easier to give that electron away and go back down to 8 to the previous shell and make that the valence shell? Or would it be easier to acquire 7 and create a stable 8 valence shell? It'd be easier to give away the 1. We're closer to 8 by giving 1 away than we are acquiring 7. So if you go to the other side of the periodic table, you'll find chloride, which is in the 7th column right next to the 8th column, the noble gases. Chloride, sodium, really happy together. If you do the math on chloride, you'll end up with 7 in the last shell. and it needs one. So rather than giving all 7 away, it's easier to just acquire one. So sodium and chloride bind together very effectively to form an ionic bond and to transfer that electron from sodium to chloride. Since it's transferred, they can remain together. They can also separate. If they separate, now we have sodium with its 11 protons, and now we have 10 electrons. So since we have one less electron, we write it as Na+, and now sodium, as with the majority of sodium found on Earth, is a positive charged atom, or a positively charged element, or a positively charged ion, all referring to basically the same thing at different levels. And more specifically, instead of saying a positively charged ion, we would say cation. In opposition to that, chloride would now be a negatively charged atom, a negatively charged element, a negatively charged ion, or more specifically an anion, because of its acceptance of one extra electron. When elements interact in this way, we then get compounds and we get molecules. Now, usually the term molecule is used primarily and it's overused. Let me provide a correct definition for what a molecule truly is. And it's when 2 or more elements of the same unite. So if 2 oxygen atoms or 2 oxygen elements bind together to form O2, which is the respiratory gas that we find in our atmosphere, not the most readily available, but we do find it in our atmosphere. Our atmosphere is actually nitrogen based. We can talk about that in a respiratory system episode. But we have 2 elements that are the same. They're bound together, so we call oxygen gas an oxygen molecule. That's very different when we look at something like water. 2 hydrogen atoms or elements and 1 oxygen atom or element. They bind together to form H2O. Well, clearly H is different than O. Hydrogen is different than oxygen. So people will a lot of times say a water molecule, but that is technically inaccurate. It better meets the definition of compound, which is 2 or more elements of differing types. So water would actually be a compound. Okay. Further from that, there's a whole bunch of different directions your chemistry class may take you, or your anatomy and physiology class, when speaking to chemistry, will take you. But other than laying down the foundation of what is organic and inorganic, you're basically there in terms of anatomy and physiology, because everything builds upon this understanding from that period of time. Now, simply if you're interested in speaking to organic and inorganic and more information on the chemistry of anatomy and physiology, we have this as a free resource to get you through, but we also have courses that we've published on our website. That website is biblicalanatomy.com. We self-sponsor, and we don't have any advertisements that come into the podcast. We ask that you consider the products that we offer at biblicalanatomy.com. Courses are there. Links to both podcasts are there. And within our courses, within our academy, we have a community as well where you can interact with fellow students, which is really nice. You can email us with the email that we provided earlier. It will also be in the show notes. If you're interested, you can simply go to the website, and the links are set up really efficiently, and it's a very simple website so that there's not a lot of confusion to direct you in the direction that you need to go. Starting next Sunday, I will be working on that website, and it will be updating over the course of the week. So if you're checking this out a little bit later, the website will look a little different, but it's still going to be built with the same concepts, the same simplicity and ease of use being paramount in its design. Tips and referrals are necessary to keep this podcast going, so if you're interested in a course, fantastic, please do that. If you're not interested in a course but you enjoy the podcast, at the least, please refer this to someone else. At the most, review the podcast or provide us a tip through the link that is provided in the show notes. So what is our take-home message for today's episode? Well, for those of you like me that love anatomy and physiology, but you're a little nervous when it comes to chemistry, or perturbed by chemistry, or just flat out confused by chemistry, we need to understand the basis of these chemical interactions, which is chemistry, to better understand anatomy and physiology. So getting over these hurdles will actually help you understand and appreciate anatomy and physiology at a greater level of depth. Let's conclude as we always do with the Lord's Prayer. Pray then like this: Our Father in heaven, hallowed be your name. Your kingdom come, your will be done, on earth as it is in heaven. Give us this day our daily bread, and forgive us our debts, as we also have forgiven our debtors. And lead us not into temptation, but deliver us from evil. Amen.